This video is a continuation of the 2.4 video, and in this video we're just going to see a bunch of different examples of domain and working with and evaluating functions. So first off, let's find the domain for each of these following functions. So first of all, we have f of x equals 1 over 1 minus x squared. So what we have here is a rational function, and this is rational because we have the variable x in the denominator. So what we need to do is we take the denominator and we set it equal to 0. We want to know when the denominator is going to equal 0. The reason we want to do this is because whenever the denominator is 0, the function will be undefined. So we end up here with x equals plus or minus 1. So what this is saying is if we input positive or negative 1 into the function, we're going to get a denominator of 0, and that's going to tell us that the function is undefined at those values, at 1 and negative 1. So the domain is everything else, everything except for positive 1 and negative 1. An easy way to maybe visualize this is to put these values on a number line, and what this is saying is the domain of this function is everywhere except negative 1 and positive 1. So again, there's two ways we can write this. We can write this in interval notation, and in interval notation it's going to be everything from negative infinity up to negative 1, don't include negative 1, and then everything between negative 1 and positive 1, and then union 1 to infinity. So that would be how we write the domain of this function in interval notation. In set notation, we would say the domain is all x such that x does not equal negative 1 or positive 1. So either way, here, either of these would be an appropriate representation of the domain. Number 2, we have here g of x equals square root 7x minus 4. This is a radical function, and it's a radical function because the input of the function, which is x, is under the radicand, or it's in a square root. So what we do is we take the radicand, 7x minus 4, and that radicand, not less than, must be greater than or equal to 0. So we solve this inequality. So 7x greater than or equal to 4, x is greater than or equal to 4/7. So what this is saying is at 4/7, the domain is everything above 4/7. So the domain is everywhere that we're shaded here on the number line. So in interval notation, the domain is going to be from 4/7 to infinity, and we include 4/7. Okay, so that would be interval notation. We could write this in set notation, and this would be all x such that x is greater than or equal to 4/7. Let's fix that, 4/7. So either way here is an appropriate way to write the domain. Number 3, we have h of x equals 15x cubed minus 12x squared plus 61x minus 5. Now this is just a regular polynomial function. There's no radicals or fractions. So when we have a polynomial function, the domain is just all real numbers. We write all real numbers in interval notation like this, negative infinity to positive infinity, or in set notation, we could say all x such that x is a real number. These next 3 questions are a little bit more challenging. This first one, j of x equals square root x plus 1 over x. Well, here we have 2 separate terms, and each term is a different type of expression. So here we have a radical, square root of x, and 1 over x is rational. So what we want to do is we want to find the domain of each of these individual pieces and then see where these domains overlap. Where the domains overlap will be the final domain for the function j of x. So for the radical function, what we do is we take the square root of x, we take the radicand, which is x, and that has to be greater than or equal to 0. Well, we have x isolated, so there's nothing else really to do. If we look on a number line, this function is going to be defined for everything greater than and including 0. So everything to the right of 0. So that takes care of that. For the rational portion, 1 over x, we take the denominator and we say that the denominator cannot equal x. So looking at a number line, everything except for 0 gets shaded here. So what we see is when we combine these, we want to know where do these shaded portions overlap. Okay, so what it looks like we have is, well, everything from 0 to the right is in both of these domains. And at 0, well, on the left side here, we include 0. On the right side, we do not include 0. So combined, we're going to say everything from 0 to infinity, not including 0. So that would be the domain in interval notation. In set notation, we could say all x such that x is greater than 0. That would be the domain here. So either way is appropriate. In number 5, we have k of x equals 1 over square root of 1 minus x. Now, this is a rational function, but inside the rational function we have a radical. So what we want to do is what's happening in the denominator cannot be equal to 0. Additionally, because it's a radical, we cannot have the radicand be greater than, or rather, the radicand cannot be negative. So what we do here is let's take the radicand, 1 minus x, and let's say that that has to be greater than or equal to 0. So what we get is 1 is greater than or equal to x. In other words, x has to be less than or equal to 1. On the number line, what we're going to say is at 1, x is less than or equal to 1. So everything to the left here. Now, we need to be careful because this is a rational expression. If we were to include this value 1, we would get 1 minus 1 in the denominator, which is 0. So if we were to include 1, we would see that this value 1 would make the function undefined. So what we want to do is we don't want to include 1. So the domain here is going to be from negative infinity up to 1, but we don't want to include 1. So that would be the domain in interval notation. In set notation, we're going to say all x such that x is less than 1, and that'll do it. So for number 6 here, L of x equals the square root of x plus 2 over x plus 3. This one's definitely the most challenging of this set here. And really the only way to see the domain here is by graphing this. So if you use a graphing utility, we would come up with a graph that looks something like this. So what we have is the red portion is the graph. Now the domain is, one way we can think about the domain is what are the x values that the graph touches. Now what we see here is that from negative infinity up to this value right here, not including that, and that's negative 3, this graph is hitting the x-axis here. And then we're going to start at negative 2, and then we're going to go to the right. So from negative infinity to negative 3, and we don't include the negative 3, union negative 2, but we're going to include negative 2. So include negative 2 to infinity. That would be the domain here. And that's written in interval notation. In set notation, we would say that the domain is all x such that we could say x is less than negative 3 or x is greater than or equal to negative 2. Either way here is appropriate. This question is, like I said, the most challenging one. You wouldn't really be expected to do this without a graphing utility, like a graphing calculator. Now the last thing we'll see in this video is working with this function, f of x equals x squared plus 4x plus 5. And let's go through a series of questions here. The first question says, is the point 27 on the graph? So x is 2, y is 7. So y is kind of like the output of the function. So we could say 7, is that equal to 2 squared plus 4 times 2 plus 5. So all we're doing is we're plugging in the point into the function, and we want to see does this point make this equation true. So is the point 2, 7 on the graph of f? To make this determination, we're just going to use this point, 2, 7, so x is 2, y is 7, and we're going to see if this point makes the function true. So we can treat the f of x kind of like a y value here, so we would say 7, is that equal to, and then let's just plug in 2 into the function, plus 4 times 2 minus 5. So does the left side equal the right side here? So 4 plus 8 minus 5, we get 7 equals 12 minus 5 is 7. So we would say yes, the point 2, 7 is on the graph for f. Next it says find all values of x such that the point x, negative 8 is on the graph of f. So let's write down what the function is. F of x equals x squared plus 4x minus 5. So what we want to do is, well, again, we know that this negative 8 is like the y value, and f of x, or negative 8 is the y value, and we can treat f of x like y. So what we'd say is negative 8 equals x squared plus 4x minus 5. So what we want to do is we want to solve this equation for x. So what I'm going to do is I'm going to add 8 to both sides. We get x squared plus 4x plus 3. And we need to solve for x. So solving this quadratic, we can just factor this. This is x plus 3, x plus 1, that's equal to 0. So x plus 3 is equal to 0. X plus 1 is equal to 0. We end up with x equal to negative 3, x equal to negative, too many negative signs, x equals negative 1. So what this is saying is negative 3 comma negative 8, okay, just plugging in the negative 3 up there for x, and negative 1, negative 8 are both going to be on the graph of f. Number 3 says to find the y-intercept of f. Well, the y-intercept, as we've seen, this will occur when x is equal to 0. So all we do is we input 0 into the function. I get 0 squared plus 4 times 0 minus 5. So f of 0 is equal to negative 5. So the y-intercept here, writing this as a point, is going to be 0, negative 5. Part 4 says to find any x-intercepts of the graph of f. Now, the x-intercepts, these are going to occur when y is equal to 0. So what we're going to do is we're going to say 0 equals x squared plus 4x minus 5. This is again a factoring question, x plus 5, x minus 1. So x equals negative 5, x equals 1 here. So the x-intercepts, we would say negative 5, 0, and 1, 0. So writing this as an ordered pair, this is what we would have. So to graph this, we've actually found 5 points that are on the graph. 2, 7, negative 3, negative 8, and negative 1, negative 8. We found the y-intercept here. This is the y-intercept, and then we found the x-intercepts. So if we go ahead and plot each of these points on the graph, that'll get us a good starting point. And we have this. Now, looks like we're going to go off the screen a little bit, but our graph would look something like this when we connect all these points. Okay, so we know that this graph forms a parabola. Whenever we have something that is squared like this, our graph is going to be a parabola. We're going to talk more about this in Chapter 3, how we graph this type of equation a little more precisely, but for right now, this is good enough. So this gets us a good idea of what the graph looks like. Then there's two other questions. Question 6 says, is f a function? Well, one way that we can determine if something is a function is by something called the horizontal line test. For a function we use what's called the vertical line test. Sorry about that. And what the vertical line test says is if we can draw a vertical line through the function, and if it hits the graph 2 times or more, then the graph is not a function. So no matter where we look, no matter where I try and draw a vertical line, I'm only hitting this function or this graph in one spot. Now imagine all those blue lines are straight vertical lines. They're only going to hit that graph one time. So because this passes the vertical line test, we would say yes, f is a function because it passes the vertical line test. Okay, and then lastly, part 7, I'll just do it on the same page here. Part 7 says find the domain. So we know that this function is just a regular polynomial, so because this is a regular polynomial, the domain is all real numbers here. And we can see that on the graph because anywhere we go in the negative x direction, all the way across to the positive x direction, the graph is going to hit wherever we go, hits the x-axis. So this graph, or this function has a domain of all real numbers, negative infinity to positive infinity.